continuing forward, there is a big problem with both of these theories. What is the big problem?
That's talent.
Oh,
Oh, wow.
so the big problem with both of these theories is the fact that neither of them these mechanics in practice tell us at the microscopic level simultaneously the position
There's no G in that.
and velocities of the molecules that we just came up with that we said would explain everything while carrying out experimentations at the human level. So, for example, in chemical reactions, so that means we need to come up with another kind of mechanics that will cover the gap between the classical and the quantum. And that mechanics that was developed was called statistical mechanics. And that's what we will be focusing on now. So statistical mechanics is kind of a new science. And the reason why it was needed is because it fills the gaps between the laws of mechanics and the practical experimental science. So it was first developed in the 19th century by multiple people. Gibbs, Boltzmann, Bose, Einstein, Fermi, and Dirac, amongst other people. Okay, so in a nutshell, why is statistical mechanics so useful? Statistical mechanics, also called statistical thermodynamics, is essential because, how do I say this? Important. Valuable because it does not deal with detailed considerations of systems. It provides a connection between macroscopic properties of materials in thermal equilibrium and microscopic behaviors and motions inside the material. Number 3, how does it do that? It takes advantage of the fact that for a system made up of many particles, the average properties of like molecules can be calculated without knowing the detailed information about individual molecules themselves. A good way to think about this is think about a train. You are sitting in a train or standing, and you are reading a book. So Newtonian mechanics will treat this scenario as a box with a center of mass, right? There will be a normal force, there will be an mg, there will probably be friction, and there will be motion. So there's, let's say, a pull force. Now, Newtonian mechanics doesn't care that you are inside this train, you are reading a book or drinking a coffee or whatever else you might be doing, right? Statistical mechanics on the other hand will care about each component. So it will treat this system as a train, the person, the book. However, the statistical mechanics will not care about the number of words in the book, because it will treat it as an ensemble. Or if you're drinking coffee, won't care about the individual coffee particles. Does that make sense? So it is more detailed than Newtonian mechanics, but it is less detailed than quantum. You guys get it?
Yes. Yes.
Okay, so think about statistical mechanics that it is more in-depth meaning than Newtonian, because Newtonian is just going to treat all of this as one mess, right? And the only time it'll care is if you walk out of the train and in fact you change the mass of your system. But statistical mechanics will treat a train, a person, a book. It will not care about the number of words in the book, or if you're drinking coffee, the copy that you have. So that is the difference between Newtonian and statistical.